In these videos, we're going to practice Gauss-Jordan elimination. In Gauss-Jordan elimination, there are two stages, a downward stage and an upward stage. In the downward stage, we're going to begin by swapping any rows that are all zeros to the bottom of our matrix. Then we're going to swap our rows so that the top row has the leading entry furthest to the left of all rows. The next step is optional. We're going to scale the top row to make the leading entry equal to 1. And then by adding or subtracting a multiple of the top row to the rows below it, we're going to eliminate any non-zero entries in the rows below our row. And finally, we're going to move to the next row down and continue this process. Once we've completed a row, we will not touch it again. So let's look at an example. We're going to practice the downward stages on the following example. So we take a look at this. So our first step is to swap any row that is all zeros to the bottom. And we can see that there are no all zero rows here. So step 1 is all done. Next, we're going to swap rows so that our leading entry in the top row is the leftmost. And this is as far left as possible. So there's no swapping needed. And it's already scaled to 1. So we are ready for step 4, which is our goal is to have all zeros in this column below 1. So we want to make everything below this entry equal to 0. Okay, so row 2 is already equal to 0 in this entry here. In row 3, we have a 2. Let's get rid of that. So to make the entry in row 3 equal to 0, we're going to subtract twice row 1 from row 3. So the notation I'm going to use is row 3 is replaced with row 3 minus 2 row 1. And I'm going to do this on this side. So row 3 minus twice row 1 is going to be equal to, so row 3 is 2, negative 1, 2, negative 3. And I'm going to be subtracting twice row 1, so 2, 2, 2, 12. Okay. So you can see I've just doubled all of the entries in row 1. And we subtract, we get 0, negative 3, 0, negative 15. So our matrix now is 1, 1, 1, 6, 0, 0, 0, 2, 0, negative 3, 0, negative 15. Okay. And now when we look at this first column, we can see we have this leading entry in the first row, and everything below it is equal to 0. So step 4 is done. And now we're going to start this process over again. Instead of looking at row 1, we're going to be looking at row 2. Okay, so moving on to row 2, if we look at the leading entries, we have this 2 here in row 2, and we have a negative 3 here in row 3. You can see that the leading entry in row 3 is further to the left than the leading entry in row 2. We want to have the furthest, the leftmost entry among all rows below our row of interest, which for us is row 2. So we're going to switch, we're going to swap row 2 and row 3. Okay, so we get 1, 1, 1, 6, 0, negative 3, 0, negative 15, 0, 0, 0, 2. Okay, so we didn't have any all 0 rows. We've now swapped so that in row 2, I have the leftmost entry among all rows below this row of interest. And next we have this optional stage of scaling the leading entry in this row to 1. So let's go ahead and do that. So I'm going to divide this row by negative 3. So row 2 is going to be replaced with negative 1/3 row 2. So I get 1, 1, 1, 6, 0, 1, 0, 5, and 0, 0, 0, 2. So scaled to 1. And now we're going to eliminate any non-zero entries in lower rows. So we're looking here and we say, okay, is there anything non-zero below it? Nope. So step 4 is done. And now we move on to the next row. So we're going to start over again, focusing this time on row 3. We swap all we swap any rows that are all zeros to the bottom. Okay, that's not relevant. This entry is the leftmost among this row and all below it. We can see now that our leading entries are marching to the right. And so this thing is in echelon form. And we're all done. So that means that the downward stage is complete. I just wanted to point out the error. It should have said 2 times R1 when we did that subtraction. So at this point we have a triangular matrix. And if possible, we would like to sort of eliminate as much mixing of variables as we can. So we're going to start out by scaling all of our rows to make the leading entry equal to 1. So each row will be divided by the leading entry, as long as it's not a row of all zeros. So let me show you an example for the next step. All right, so in this example, you can see we have these leading entries. We're going to call these things pivots. They're all equal to 1. Below them, we have zeros, right? Okay, so what we're going to do is we're going to start at this bottom row. And what we want to do is clear out the entries that live above this bottom leading entry, this bottom pivot. What this translates to is like when we had that system of equations where we had z's in all of them, but we knew z was equal to 1. So this is sort of removing z. Okay, so the way that we're going to do this is we are going to add and subtract multiples of this bottom row to the rows above it. So whatever this first star is, we'll multiply the bottom row by it and subtract. So we're using the replacement operation again. Once we've done that, our cartoon is going to look like this. Okay, so we have all zeros above this leading entry. Now we move on to the next row. Okay, we find our leading entry, and we're going to clear out everything that lives above the leading entry by, in this case, we would take R1 minus star times R2. Okay, and this will put us in this form. And we're going to consider this done when we are out of rows. So we arrive at this leading entry, and there are no zeros above us. There's nothing above us, so we can't continue. A matrix in this kind of form, where the leading entries are all equal to 1, and they march to the right, and in each column we have only one non-zero. In each of these columns containing a leading entry, it's the only non-zero one. This is something we would call reduced row echelon form. And if it has a form, if it's in this form, then it's easy to solve the system by hand. So we can translate it back to our variables and be done with it. Okay, so let's look at an example. Okay, so now we're going to be working upwards. So in the first step, we showed that this original matrix was row equivalent to the following echelon form matrix. And now we want to put it in reduced row echelon form. So what that means is that if we look at our leading entries, you can see that they're moving to the right. And what we would like is that they're all equal to 1, and that in each column containing a leading entry, it's the only non-zero entry in that column. Okay. So our first step is always going to just be this, this one here, to make all leading entries equal to 1. So we're mostly done here. All we want to do is to multiply row 3 by 1/2. Okay, so now when we look at our pivots, or our leading entries, we can see that they're all equal to 1 and they're moving to the right. Okay. So the main idea here is that we're going to start at the bottom row, and we're going to eliminate any non-zero entries above our pivot. So here, our non-zero entries above the pivot are 6 and 5. So we're going to replace row 2 with row 2 minus 5 times row 3 to get rid of this 5. Okay, so this changes the 5 to a 0. Okay. And next we want to get rid of this 6. So we're going to do that by replacing row 1 with row 1 minus 6, row 3. Okay, so now if we look at this, the entries above this pivot, we can see that they're all 0. So this is the only non-zero entry in this column. Okay, moving on to row 2. If we look at its leading entry in row 2 is 1, and above it we have a 1. So we are going to eliminate this 1 by replacing row 1 with row 1 minus row 2. And now we can see that we have all of our leading entries are equal to 1. They're moving to the right, and any column that has a leading entry in it is the only non-zero entry in that column. So if we look at column 1, this this pivot is the only non-zero entry. If we look at column 2, again, our pivot is the only non-zero entry. And if we look at column 4, our pivot is the only non-zero entry. And so this thing is now in reduced row echelon form.